As nations race to unlock the potential of space exploration and satellite innovation, one institution is quietly emerging as a pioneering force in Taiwan's space ambitions. This academic lab is behind the country's first ever lunar mission and is training the next generation of space scientists. We'll be speaking to the man who led the mission. I'm Divya Gopalan and you're watching Connected on TaiwanPlus. Thank you so much for being on the program, Professor Chang. Let's start with your university department. Tell us about CAPE and how it's come to be at the forefront of space studies and research in Taiwan.
So CAPE is our university space center here at NCU, and it's designed to unite faculty across multiple departments who have a common interest in space-related projects to facilitate coordination and collaboration between people from different fields. Space is a very diverse field. You need people of all different sorts of backgrounds and specialities. So having a common framework to work under and also common resources that we can use in addition to resources that we apply for and acquire ourselves basically allows us to do much more complex projects or to work on new fields that we would not have been able to do just on our own. And so CAPE is actually modeled off of several other university space centers at other universities around the world that we've seen. Some examples include the Applied Physics Laboratory at Johns Hopkins University, the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder, where I got my PhD, and also the Jet Propulsion Laboratory at Caltech. So the idea here is basically to have a dedicated research center, again, that brings people together and we can work together on new challenges and to build new capacities that we did not have before.
You lead the university's Upper Aerodynamics Laboratory. Can you tell us what it does and what part it plays in Taiwan's space ambitions?
Well, the Upper Aerodynamics Laboratory is the name of my research group. Typically, all the professors here have their own research groups, and of course we all have some snazzy title for our research groups. In the case of ours, it started from the fact that when I first came to NCU, I was working primarily on upper atmospheric physics, understanding how the air moves, circulates, what affects the structure of the Earth's upper atmosphere, and how that in turn affects things like the drag spacecraft in low Earth orbit experience, and also how the ionosphere affects satellite communications and navigation. So UADL, as we call it, has grown considerably since we first started. When I first started as a new faculty member here, I only had one graduate student, and now we have a team of close to 15 to 20 graduates and undergraduates working on much more complex projects than we ever did before.
Your latest DSRP mission looked to go beyond the lower Earth orbit. Can you tell us the significance of that and the challenges you faced in doing that?
Sure. Well, space is hard, no matter where you go. But I have to say, going out of low Earth orbit, where the vast majority of satellites are, and where spacecraft are closer, and to a certain extent are still shielded by the Earth's upper atmosphere and magnetic field, and this is actually somewhat easier than going beyond, going higher, going further. Because once you leave low Earth orbit, first of all, the natural environment changes and becomes much more hostile towards human technology or even human beings. Basically, the further you go from the Earth, the less of a role the Earth's shadow plays. If you're in low Earth orbit, your spacecraft is constantly going in and out of the Earth's shadow. So the amount of heating the spacecraft feels is always changing. So compared to a spacecraft far away from the Earth that isn't really affected by the Earth's shadow, basically you're going to have much more extreme temperature variations in the higher orbits. So basically parts of the spacecraft pointed at the sun are going to reach extremely high temperatures, and pointed at cold space are going to reach extremely low temperatures. And you have to figure out a way to ensure that your spacecraft or your payload will still function in this environment, especially if it's located on the outside of the spacecraft, like our payload to the moon was. Another challenge is the radiation environment. Even in low Earth orbit, space is a high radiation environment because a lot of energetic particles and electromagnetic waves, highly energetic ones like X-rays or gamma rays, are normally shielded by the Earth's upper atmosphere. And particle radiation, like the plasma that the sun constantly emits, the solar wind, that is normally, part of it is deflected by the Earth's magnetic field. So if you're in low Earth orbit, you already have a lot less shielding from the upper atmosphere. If you go far away from the Earth, even potentially outside the Earth's magnetic field, or at least to where it's weaker, you're going to have much higher radiation doses and dose rates that you have to contend with. This degrades electronics and also shortens their lifespan. And in some cases, it can also cause devices to prematurely fail due to if they're hit by, say, an energetic particle. So these are all challenges that we have to deal with. And it's also challenging from a resource side and also the operational environment. So the further you are away from the Earth, first of all, the further the signals we use to command the spacecraft and the signals we use to send data back to Earth, the longer the time delay for communications on both sides. And at the same time, of course, because we're very far away, the signals are much, much weaker. So we can't send data as fast as we might be able to for a spacecraft in a lower orbit that's closer to us. At the same time, the further you go away from the Earth, the more fuel it takes to launch your spacecraft. And so this constrains the size of the spacecraft. You normally don't have as much mass budget to work with for a spacecraft going to the moon compared to, say, a spacecraft in low Earth orbit. And at the same time, because of the distance, we also have to deal with the fact that there's a lot less we can do in terms of diagnostics or even potentially trying to fix things if something goes wrong. The most we can do is command the spacecraft, but sometimes there are the most common way of solving problems on a spacecraft is often to just power cycle the spacecraft, to command the spacecraft to reboot. But beyond that, there's less and less that you can do to intervene if something goes wrong.
Okay, let's talk about the Deep Space Radiation Probe mission. Resilience, the lunar lander developed by the Japanese space startup iSpace, which carried the DSRP, lost communication and did not achieve touchdown on the moon.
20 meters, final approach. 10 meters. And our simulation might have lost its connection with...
Can you briefly explain what happened and what your takeaway from that experience is?
So DSRP was actually the first time we tried to build a payload that was going to go beyond low Earth orbit. And in fact, it's the first time any Taiwanese payload, for that matter, has gone outside low Earth orbit. And also, it's the first Taiwanese payload to reach the moon. So DSRP is designed to measure the radiation dose and dose rate, how quickly radiation dose accumulates between the Earth and the moon, and also to understand how that affects electronics we commonly use on spacecraft. So this is important because if you want to measure radiation dose and dose rate, this is not something you can do using remote sensing methods. To measure these parameters, you actually have to physically build an instrument and fly it to the regime that you want to sample. And so this is important for space mission design and also spacecraft design, because in order to understand the radiation environment and the expected dose that we will have to be able to tolerate throughout the course of a mission, we need to first understand what that is in the regime that we're going to visit. And of course, the further away you go from Earth, the less and less data we have. So that was one major motivation in terms of why we decided to build DSRP when the opportunity for a rideshare aboard a commercial lunar lander from the Japanese firm iSpace opened up. It was also based on our experiences with our own first small spacecraft, IdeaSat. IdeaSat was our first small spacecraft. We successfully assembled and qualified it, and it was successfully launched. And we got about 2 months of data from the spacecraft out of the original planned 6 months. And later, through analyzing our flight data, we found this was due to the fact that our self-designed electrical power subsystem of the spacecraft was not as radiation tolerant as it should have been. So that shortened the life of the spacecraft, but was also very illustrative to us in really understanding the effects of space radiation on spacecraft. It's one thing to read about it in a textbook, but it's a whole other thing when you have a team of students, well, a team of professionals actually, working together, running into unexpected problems, both hardware and software, and then just realizing, wow, we didn't realize it was going to be this severe. Or maybe we did realize it, but we didn't realize it was going to be this intense.
And how did you get the payload onto the moon?
Right. So the objective of the spacecraft, iSpace's Resilience lander, was to, again, travel from the Earth to the moon and ultimately perform a soft landing on the moon.
Right.
By soft landing, that's distinct from a crash landing or a hard landing, yeah. For us, though, our objectives, while landing on the moon and getting data there was one of them, it was not the only one. And similarly for iSpace, they had multiple objectives besides just landing on the moon. They wanted to qualify their lander, they wanted to determine whether their flight software worked, and so forth. So for us, our main objective was to measure the radiation environment between the Earth and the moon, and also in lunar orbit, and then ultimately if the landing was successful on the lunar surface. And so we actually got 5 months of very good data. We were turned on a few days after launch, and we were active over 97.7% of the entire mission. All the data was returned to Earth. We're currently analyzing it and planning to publish it. So we got very good information about seeing how quickly the radiation dose accumulated when we were passing through the Van Allen radiation belts and when there were solar radiation storms. But also, even when there weren't any solar radiation storms, and even when we were outside the radiation belt, we just noticed a constant increase in dose. Not fast, but much higher than you would expect on Earth. And this is significant because for future missions flying to the moon, or even beyond, to Mars, this is the background radiation dose rate from cosmic rays that we are going to have to face, that we are going to have to design for, in order to ensure that our spacecraft and even astronauts will not suffer detrimental effects throughout the course of the mission.
Was that the key takeaway from this mission for you?
That was one of the key takeaways, basically. So again, we were actually able to basically quantify the expected dose from radiation belt transit, from solar radiation storms, but also just that background value in deep space.
Right.
Yeah.
And from the data that you have been now going through and trying to break down, what are you finding that you didn't know before?
Well, first of all, that background value, while it's something you see in textbooks, it's a whole other thing to see it in data that from an instrument that you built.
Right.
And also, one of the other things that we didn't expect was, so one of the objectives of the payload was to measure the effect of high energy particles from cosmic rays or trapped in the radiation belts on computer memory. And so we did measure several of these events, but right now we're still trying to figure out if we can attribute some particular source to each individual event.
Right.
Some we might have an idea of. Maybe there was a solar radiation storm. Maybe it was due to the fact we were passing through the radiation belts. But others, if there's no immediate event, then at the moment the best guess is just cosmic rays. High energy particles are coming into the solar system from all directions. Yeah. So this is something we're still learning as we go along, and it's something we're trying to untangle. But again, we want to get this published so we can get feedback from the scientific community.
I understand there's another mission in 2028. Can you tell us about that mission and the collaborations that are part of that mission?
Right. So a couple of years ago, I think also around the time that our DSRP project kicked off in 2022, Taiwan Space Agency, TASA, basically issued contracts to 4 or 5 different universities in Taiwan to build payloads intended for a lunar lander. Although one interesting thing is at the time they didn't actually have a contract with a lunar services provider. We went first on that, and
that was with the resilience.
Yes, that was with iSpace.
Yeah.
And so one of the payloads is called the Lunar Vector Magnetometer. It was developed by one of my colleagues, Professor Yahui Yang, in our department, and it's designed to measure the moon's magnetic field. This is important because, unlike Earth, the moon doesn't have a strong planetary magnetic field. It's much weaker and more localized. So this is important because if we ultimately want to establish bases on the moon to be inhabited, areas with stronger magnetic fields will provide a little more shielding from space radiation compared to unshielded areas. So I believe last month, TASA, I understand that several of these teams have already delivered their payloads to TASA. And just last month, TASA finally signed a contract with also iSpace to launch 2 of the payloads, including the one from my colleague, on the iSpace lander going up in 2028.
Right, okay. It was 400 grams, wasn't it? Your instrument.
Our
Can you
payload
tell
was
us
400
about
grams, yes.
the payload built by it was built by both university and professors. What did it take to get it off the ground, especially from a university? I understand you partnered with a commercial entity, but can you tell us if that is kind of the way forward for research?
So for DSRP, it was developed by one faculty member, me, and a team that at most comprised 5 students, although they did receive additional support and advice from other students in my lab also working on small satellite projects. So it was challenging, and the team originally started from 2 students who were actually only second-year undergraduates at the time, but they stuck with the project, and we brought in new students as the number of specialties we needed increased. But at most, the core team was never larger than 5 students. But they were all very committed. They all worked very hard to design and implement something that could successfully pass qualification testing. And after 5 revisions, they delivered the flight model, the version that we actually flew. So it was a very good learning experience for everyone, and also helped us develop capacities that we didn't previously have. Designing for deep space, thermal control in deep space, and also designing radiation-tolerant electronics, but also on the mechanical side, designing mechanical structure for a payload that could withstand 30 times its own weight, but at the same time, all combined, be less than 400 grams in mass. So those were all major challenges, but I'm very happy to say the students delivered. iSpace was also very good in terms of providing additional advice and guidance for our students, and they also put in some extra treats along the way, including, for example, setting up networking sessions where our students could meet with their younger engineers and understand their professional developments, and which was quite inspirational for everyone involved.
How do you hope this DSRP mission that you have just completed will contribute to Taiwan's overall space program or help propel it forward?
Well, in several ways. First of all, of course, developing the capacity to design and build for lunar missions and deep space, increasing our capacities in terms of radiation testing and designing radiation-tolerant electronics. Actually, an outgrowth of that is we actually now have a joint industry project with a computer memory manufacturer in Taiwan to work with them to qualify their products for space and perform radiation testing on that. So that was one direct effect. And at the same time also building the connections with international commercial space firms that are playing a bigger and bigger role. So although more and more people need to fly something into space, not everyone has the ability or the time or the willingness to build their own spacecraft. So being able to, for example, deliver your payload to a commercial provider for a rideshare launch is definitely a very viable way moving forward. And again, will serve to increase the access to space for everyone. Of course, in our department, we still want our students to have the spacecraft design and build experience, but even we realize that given the number of missions that we have, we can't afford to implement all of them completely by ourselves. And it's good to have commercial partners. So this is also an important step forward, and also it increases Taiwan's visibility in the space sector internationally.
Tell us about getting information from the payload, that data now that you are studying. How do you get that information, and what are the challenges in getting the research on the ground?
Mm-hmm. Well, like any space mission, the payload is connected to the spacecraft computer, and the spacecraft computer constantly pulls the payload for data, which is then saved to onboard memory on the spacecraft. When the spacecraft is ready to communicate with the ground, basically the spacecraft receives a command sent from a ground station, and then the spacecraft onboard computer reads the data from memory and then replays it, basically transmits it back to Earth where it's received, and then the signal demodulated, decoded, and then the data is ultimately delivered to us.
Right. Tell us about Taiwan's advantage. You know, Taiwan is a world leader in semiconductors. How is that playing into the space program, or is that playing at all into the space program?
It is. So in Taiwan, due to our strength in terms of electronics, including semiconductors, but not exclusively so, including the entire electronics manufacturing and testing supply chain, this is very comprehensive in Taiwan. So compared to colleagues in some other countries, for example, it's much easier and cheaper for us to acquire the components we need to fabricate things like printed circuit boards or to find providers of different testing or qualification services. So this is one strength that we have. We also have a lot of facilities that can be used for space, even though in the past we have not. For example, in Taiwan, we have access to very high-end radiation testing facilities that were that originally were used primarily for medicine or for instrument calibration, but can also be applied to space radiation testing. And so we've often received inquiries from colleagues in other countries in the general East Asian area who are interested in using our test facilities because they don't have access to that in their countries, or if they wanted to test at similar facilities in, say, North America or Europe, it would be much, much more expensive and much, much longer wait times. And so these are some of our strengths. Of course, previously in Taiwan's commercial sector, there was very, very little exposure to space. Mm-hmm. So a lot of companies that want in have the ability to design for space, but don't know what to design for, or they don't know what the operational constraints are or what the space environment is like. So these are all things where I think, as our university was one of the first entities in Taiwan to start working on space science back in the 1960s, this is one aspect where NCU can and has helped a lot of companies interested in developing space-related products, or even in the case of some larger conglomerates, developing in-house space-flight capacity, have partnered with us where we can share our experiences, and in some cases, we can mentor their engineers in terms of the space engineering process, while their engineers can also mentor our students in terms of more specific things like, say, electronics design or radio communications and so forth.
You've been collaborating with other departments or other entities in different countries, including India and the US. Can you just give us an idea of what that collaboration entails?
Sure. Space is a very international field, and of course, being hard and complex, it's always helpful to be able to have partners who can, where we can each share what the resources and the know-how that we have. And so for us, when we decided to start our university small satellite program back in 2015, we had the opportunity to partner with the University of Colorado Boulder, my alma mater. Mm-hmm. They're extremely experienced. They're a principal NASA contractor, and they've sent payloads and spacecraft to every planet in the solar system, as well as Pluto. And then also one other partner in the consortium back in 2015 was the Indian Institute of Space Science and Technology, IIST. So IIST is pretty unique in that it's an institute of higher education that's under India's Department of Space. So they have a very close connection to the Indian Space Research Organization, ISRO, and in fact, a lot of their students just end up moving into ISRO after they graduate. So they have access to ISRO's resources and also launch opportunities by ISRO launch vehicles. And in our case, we had a strong background in space science and also payload design and qualification, so that we were able to bring that to the table. And so with this three-way collaboration, we were each able to contribute our strengths, our resources, and basically build something, I would say, much more capable compared to if we each did it alone. And at the same time, it was a very valuable networking experience for our students, where they worked on the projects with students from other universities in other countries and get to understand the global space environment.
Many countries rely on large foreign rockets for launch, and you also, your project also relied on an international kind of a rocket launch too. But Taiwan does have an indigenous launch vehicle program. How advanced is it, and is this something you can see working with in the future?
Yeah, TASA does have an indigenous launch vehicle program, and of course, and then also on the commercial side, T-Space also has subsidiaries in Japan and Australia, and they're also working on a small satellite launch vehicle. In fact, just last month, T-Space was actually able to perform a successful test launch of their rocket from Australia, where it flew up to 80 kilometers, which is a pretty significant step in launch vehicle development. TASA's, I believe, is at an earlier stage, but I think in both cases, countries around the world are starting to realize the importance of having sovereign space capability. Mm-hmm. This includes being able to, on the downstream end, utilize the data and services that spacecraft can deliver, and on the upstream end, designing spacecraft and also in this case, launch vehicles which control access to space. Although we can get access to space on launch vehicles from other countries, and many times at very economically competitive prices, it is still sometimes a good idea to have the sovereign capability so you're not solely reliant on others, or at the very least, even if you want to use services from other providers, you're in a much stronger position in negotiations. So we've seen over the last couple of years several countries working to develop sovereign launch capability, either by government agencies or by private companies. Mm-hmm. So for example, we've seen this in Australia. We've seen this in South Korea. They actually recently launched their own KSLV launch vehicle for the second time. But in all these cases, though, it's important to stress satellites are not easy, launch vehicles are not easy. Mm-hmm. And if we look at the new launch vehicles that are now operating, typically they've taken a decade, if not more, time to develop, and in many cases through multiple failed launches. But again, in space, that's how you grow, that's how you learn. You fail, you analyze why, you figure out how not to let that happen again, and that's a lesson learned. So the term lesson learned is something that you're going to hear a lot of in the space sector, because everyone's always experienced them, and usually not in a happy way. Mm-hmm. But they're very important in terms of growing and learning.
In your opinion, what should Taiwan's goal be when it comes to space exploration? Is it about communication, or is it more about, like you were doing, payloads to the moon, more data gathering? What should be Taiwan's near-term goal?
Well, I think in terms of Taiwan's near-term goal, I would say on the government side, of course, the focus at the moment is very heavily in terms of national needs and priorities. This includes satellite communications for communications resilience, but also optical remote sensing, which is important both for civil and also national security purposes. Having a remote sensing satellite that we operate ensures that we can image whatever we want, as opposed to perhaps being constrained by a third-party commercial provider. And of course, TASA has been working on a launch vehicle program, which is still in its very early stages, but that's going. And then, of course, on the commercial side, you have T-Space. On the commercial side, I think a big part of it is the new entrants into the space sector obviously want to deliver products they can sell. So for them, being able to understand the market, developing the international connections they need, and competitive products on the international market is very important to them. Space is a very big field, so it's very difficult commercially to be profitable if you service only one country. So also developing these international connections and knowing the global space market is important for our commercial entities. And on our side, in academia, of course, talent cultivation, training the next generation of space professionals and giving them the opportunity to learn hands-on and also connect with their peers on the world stage is very important to us. And also, scientific exploration is also very important for us. Better understanding both the Earth from space, but also the effect of space on Earth, both in terms of the environment, in terms of our technology, and better understanding why the solar system is the way it is. What conditions led to the different environments in the different planets in the solar system, and what does this comparative planetary science tell us about our planet? And so it's interesting to note that, like a lot of countries, Taiwan, we got our first ticket into space through science, because science is viewed as a global good, much less controversial than something like, say, a rocket that could also be used as a ballistic missile. And so for a lot of countries, including Taiwan, our first steps into space were through space science. And then from there, we learned, we grew, and we started to develop more capacity.
Right. So you may have talked about this already a little bit, but if you were to very, I guess in a nutshell, explain or give us a sense of what's the moonshot goal for CAPE going forward? What is the next, basically the next achievement you hope to hit?
We have quite a few very exciting projects that are currently underway. So in the near term, two very interesting projects that we're working on, not exclusively, of course. One is related to secure optical communications. So we're working with our colleagues in our Department of Optics and Photonics on designing and building a communications payload that allows you to communicate by laser, so much higher data rates than you could by RF. But at the same time, we also want to use a method called quantum key distribution, QKD, to ensure secure communications. And what that does is basically, in order to encrypt any information, you need a key. So both the sender and the receiver have to have that key in order to encrypt and then decrypt the message. Problem is, if someone else gets hold of that key, they can also decrypt the message. Quantum key distribution is a method whereby, using the principles of quantum mechanics, the sender and the receiver will know if someone has intercepted and read and knows the contents of the key. So if they detect that, they can decide not to send the message using that key and to switch to another key. So this is very novel technology that has only been demonstrated in space once by a Chinese spacecraft, Mozi, in 2016. A lot of people are interested in implementing this around the world, but as you can see from the fact that no one's launched anything like that since then, it's hard. Right. So if we can pull this off, then it will be a major advance in terms of our capabilities, both in terms of optical communications and also secure communications. Another very exciting project that we're working on right now with colleagues in our Department of Biomedical Science and Engineering is space life science, developing the capacity to design experiments for microgravity and also for radiation environments, understanding how these affect biological organisms, and in doing so, giving us a better idea of how biological systems work, how our own bodies work, and how they respond to the microgravity and high radiation environments of space. So compared to a lot of countries, Taiwan is actually a very, very recent entrant into the space life sciences field. So this only started about 2 or 3 years ago. So for us, we're working with them to help them build up their capacity to design experiments that they can fly to the International Space Station or small satellites regarding biology topics, and also at the same time developing some of the instrumentation that you would need to quickly perform experiments in microgravity. For example, we also have colleagues in our Department of Mechanical Engineering who are working on what are called biochips. Basically, you can think of it as a lab on a chip. You know that typically for a biological experiment, the stereotype is you have someone in a lab coat and goggles with a bunch of test tubes and a clean bench, and then basically an eyedropper, and then basically piping things around like that. In the case of a biochip, basically we design basically a platform where the samples you need, the reagents you need are all there, and at the precise time when the chip is, for example, inserted into a machine, then all those go to where they need to go, and then we have the sensors to read the data and know the results. Yeah, so that's also a capacity related to space life science that we're also developing here at NCU. So this is very exciting for me because, again, it's something that in Taiwan we did not previously have. But of course, it's being utilized more and more because different entities and different companies are realizing that there's more and more useful things you can do, both in terms of understanding biological organisms, in terms of pharmaceutical design, and in terms of material science that you can do in microgravity. And so, again, this is something that's quite new to Taiwan, and it's very exciting to do what I can to help it take off, and also to build the international connections between our colleagues with international providers or partners who could potentially work with them on this.
And for all this research to advance, you do have to get another payload on another shuttle and test it out in space, I'm assuming.
Yes, so for these microgravity experiments, you need to typically design some type of payload or some type of experimental instrument if you're going to send it to the space station. But of course, even that's non-trivial. First, you need to make sure it will deliver the data you want. And at the same time, you need to know the conditions under which to perform the experiment to ensure you're going to get the result that you want. What temperature to use, what different density of different reagents or concentrations to use. And of course, launching anything into space, while cheaper than before, is still expensive. So you want to make sure that it's going to work in the way that you intended when it goes up. So the amount of reliability in terms of design and qualification, whether we're talking about a microgravity experiment payload or literally any payload, any spacecraft, is much, much higher than we would usually expect for a device to be used on the ground. And also, besides the technical challenges, there are also regulatory challenges. So if you want to fly an experiment on the International Space Station, for example, because there are humans on board, there's a very, very strict review process for the different chemical compounds, the components you can use, the types of devices that you can use in your payload design and so forth. And also, navigating that by itself is also a process that needs to be learned if we are going to design and implement various microgravity experiments for space life science or material science or so forth.
All right, we're running out of time here, but as a final parting shot here, for those of us watching in Taiwan, what is the main reason you think that they should know, or what we all should know and think about when it comes to space exploration, and why it is important for Taiwan?
I think one important thing that I hope everyone knows is space is not that far away. In fact, it's even closer. It's probably closer than you think. So if you think about it, we all have space technology in our pockets. We all have smartphones. On your smartphone, there's a GPS receiver, and that includes highly sensitive antennas, chips to perform modulation and demodulation, and also the types of signal processing and calculation methods needed to implement this. If you look at, if you watch a weather report, a lot of the data that was used to feed into the forecast models to produce that weather forecast came from satellites, came from space. We've all navigated via, for example, Google Maps. We've seen how that fuses both GPS and also satellite imagery. And of course, at the same time, we use space-based platforms and technology for so many things, like remote sensing, which can also be used for disaster relief. It is. In fact, during the recent floods in Hualien, our university's Center for Space and Remote Sensing Research immediately following the flooding, started rapidly turning around satellite imagery of the affected area that could better allow rescue and also relief and reconstruction efforts. At the same time, space is important in terms of, for example, communications resilience. Taiwan is currently reliant on 15 submarine fiber optic cables for all of our international communications, and those can be cut by both natural and sabotage, yeah, natural causes and sabotage. And also at the same time, I think a lot of people don't realize is that since the barrier to entry to space is so much lower now, that means we can launch more stuff. We've all heard of these mega constellations of satellites in low Earth orbit, for example, SpaceX's Starlink or many of the other communications mega constellations. What a lot of people don't realize is these spacecraft, compared to like the case where you only have one large spacecraft that can be designed to be extremely robust and have a useful lifespan of, say, 15 years. Mm-hmm. These mega constellation these individual spacecraft of these mega constellations, it would not be economically feasible to design them to that level of robustness with that sort of lifetime. So for these mega constellations, there's actually a very rapid launch and replacement cycle. Mm-hmm. And this is very important because then you want to get the unit cost of each spacecraft down. And as it turns out, if there's one thing that Taiwan's electronics sector is very good at, it's mass producing electronics to a high level of quality and at the same time also cutting costs. So that is actually, in fact, one of the reasons why a lot of companies in Taiwan are interested in moving into the space sector now, including a lot of our commercial OEMs. And at the same time, what a lot of people don't realize is a big part of the space economy is based actually on either goods and services delivered to people on the ground or equipment that is designed to be used on the ground. Mm-hmm. So if you think about it, your smartphone with your GPS is space technology. If you are going to use, say, a satellite communications network, you need an antenna on the ground, you need a router, you need a modem. These all have to be mass produced. Mm-hmm. And that, in fact, is something that that, again, Taiwan's industry is very good at. And so what I'd like more people in Taiwan to realize mm-hmm. is, again, there are more and more entities in Taiwan getting involved in space. It's important both from a national security perspective, but also a commercial perspective, and also in terms of a capacity building perspective. So the reliability that you need when you're designing something for space is so much higher. And so by developing this capacity, this ability in Taiwan, this ultimately builds up a big talent pool and a big pool of know-how that can be applied both to space but also other non-space fields. And of course, space encourages the growth of new capacities and new knowledge, both about our environment and also how we as human beings respond to it.
Thank you so much. Space is in our everyday lives. I guess people have to remember that. It's not something that's out in the stars and over in the moon. Thank you. Appreciate it. Professor Loren Chang, thank you for explaining things so well and breaking such complex bits of information in such a digestible way. Appreciate it.
Thank you very much.